And we're back for round two. Let's go over questions 24 through 30. So question 24 wants you to prove the parallelogram rule, which says that u plus v squared, or the norm of u plus v squared plus the norm of u minus v squared equals 2 times the norm of u squared plus 2 times the norm of v squared. So the key thing to remember here is that the norm squared of a vector is just that vector dotted with itself. So again, these are all vectors. So u plus v squared is going to be u plus v dot u plus v. And u minus v squared is going to be u minus v dot u minus v. So now I just use those properties of dot products. First, I can do, it will basically work just like FOIL because of the properties of dot products. So I would do u dot u first, outer, u dot v, inner, v dot u, and last, v dot v. Similarly, on this side, we would get u dot u minus u dot v, because u dot minus v, minus v dot u, inner and last, minus v dot minus v is going to be plus v dot v. So now let's do some simplifications here. U dot u is the norm of u squared. U dot v plus v dot u, well, u dot v is the same as v dot u. We proved that on our true false, our first true false. U dot v equals v dot u. So this is going to be 2 times u dot v plus the norm of v squared, v dot v. Now looking here, u dot u is the norm of u squared. U dot v minus v dot u are both negative. This is going to give us negative 2 u dot v plus the norm of v squared. This term cancels with this one. Combine these like terms, we end up with 2 norm of u squared plus 2 norm of v squared, which is what we wanted. All right, on to 28. So suppose y is perpendicular to both u and v. Show that, so this word is perpendicular or orthogonal. Show that y is perpendicular to every w that's in the span of u and v. So if w is in the span of u and v, we can write it as a linear combination of u and v. So that's where we're going to start. So if I want to prove that y is perpendicular to every w, I have to show that y dot w equals 0, because we know that any two vectors are orthogonal if and only if their dot product is 0. So let's actually we're going to end up taking the dot product of y with w. But first, I want to make two other important comments. Y is orthogonal to u and y is orthogonal to v. So we know that y dot u equals 0 and y dot v equals 0 because they're orthogonal. And we're going to use both of these facts. So now if I do y dot w, this is going to be the same as y dotted with c1u plus c2v, because w equals c1u plus c2v. So now I use the properties of dot products. This is going to be y dotted with c1u plus y dotted with c2v. That's the associative property of dot products, or distributive property of dot products. Now the scalar can pull to the front, so this is c1 times y dot u plus c2 times y dot v. And from star, we know that this equals 0 and this equals 0. So we showed that y dot w equals 0, which means y is perpendicular to w. And since every w in the span of u and v is going to look like this proof works for all of those w's. All right, let's move on to question 30. In question 30, we're taking a vector in w perp and a vector in w. And we want to show, or we want to first claim is that z dotted with u is equal to 0. So z is in w perp means that z is orthogonal to everything in w. U is in w, so z is orthogonal to u, which means their dot product is 0. So that is just basically showing the claim that the textbook gave you in the hint. You didn't have to do this, but I wanted to make sure you understood where this is coming from. So now if we pick any scalar, then we want to show that c times z is perpendicular to w. So again, we use our regular trick. We have to show that c times z dotted with u equals 0. Well, c times z dotted with u is c times z dotted with u. So that's going to equal 0 because z dot u equals 0. Now the next step tells us to take z1 and z2 in w perp and pick a u that's in w and show that z1 plus z2 is perpendicular to u. So how do we show two things are perpendicular? We take their dot product. So we take z1 plus z2 dotted with u. This is going to equal z1 dot u plus z2 dot u. And this equals 0 and this equals 0 by the same fact because z1 and z2 are both in w perp. So what can we conclude about z1 plus z2? If they're perpendicular to everything in w, then z1 plus z2 is in w perp. So far we showed that cz1 is in w perp and z1 plus z2 is in w perp. Our ultimate goal is to show that w perp is a subspace. So what else do we need to do to complete the proof? Well, we need to remember what a subspace is. So remember that a subspace is any set of vectors where the 0 vector's in it. For every vector in that set, scalar multiples are in it. And for every 2 vectors in that space, we can add them and get another vector in it. So in part A, we showed that when we take any scalar and multiply it by a vector, that will be in the subspace. So we did this one. In part B, we showed that the sum of any 2 vectors in w perp remains in w perp. So we did, for any 2 vectors in w perp, the sum remains in w perp. We did this one. So what do we need to show to complete the proof? We need to show that the 0 vector is in w perp. So we need to show is 0 orthogonal to w. So let u be in w. U dot 0 equals the 0 vector. Or equals 0, sorry. Anything dotted with the 0 vector equals 0. Which means that u is perpendicular to the 0 vector. So the 0 vector is in w perp, and so now we're done. So I'll do question 32 in a separate video, but I hope that this was helpful and informative, and I'll see you all soon.